Welcome back to ECE 441A, 541A. Not next time, but the time after that, we will be having our exam. The next time we meet is the day that your homework assignment is due, homework number 2. Friday is your exam. There's a list of topics, but essentially study or in addition to what you've already looked at as far as homeworks and lecture notes, you should be strongly encouraged to look at the old practice exams and make sure you're comfortable with those problems and how they're laid out. Lab number 1 is available, I believe. I think somebody may have ventured in and executed it. We may have a slight change in the way that you log into the system, but if you do not yet have a teammate or teammates, go ahead and sign up for a time slot, and maybe somebody could self-select, or you could pair up at common times that you're both or all three are available. That's, I think, how we will go about assigning people that don't yet have teammates. Today, what I want to do is pick up or continue developing system identification techniques, and in particular, techniques for underdamped second-order systems. Last time we talked about first order, and now you can look at time domain or step response data and pull from that information transfer function representations. We want to do the same thing for second-order systems, and to get us started, to start us thinking about what you're comfortable with, or what I hope you're comfortable with, let's now look at you finding the time domain expression for little y sub a of t, which is now the inverse Laplace transform of this ratio of polynomials. And you might note that this particular ratio of polynomials, there are no finite values of s that cause the numerator to vanish. There are no zeros. And I hope you're starting to see what's downstairs. So now try to find little y sub a of t, or just write it down if you have your Laplace tables memorized. That's what I'm hoping you start to do, is when you see these, you can almost immediately envision what that looks like. Everyone get an answer? Do you know where to start, or what you were doing with respect to inverse Laplace transforming that? And I've written the denominator in a special factored form to help us identify what the time domain response might actually look like. Did you see the pole locations in this transfer function? Is it clear where your poles are located? If you now needed to set the denominator equal to 0 and evaluate for values of s, where are your poles? And in particular, where do you locate those in the complex S plane? Anybody want to venture an answer on a Monday morning, where are your poles located? And they are actually staring at us explicitly in that special way that I have it factored. I have S plus sigma quantity squared plus omega sub d squared. The real part is the minus sigma, and then the imaginary part is the omega sub d. Our poles then are at this distance into the left half plane of sigma at minus sigma, and they are at vertical locations plus and minus j omega sub d. Our poles, then, we have two of those. We don't have any zeros. We don't have any open circles. There's our poles. And now what would little y sub a of t look like? And I've sort of hidden the numerator, which is helpful in inverse Laplace transforming. Hopefully, when you see poles, two poles that are complex conjugates into the left half plane, a distance minus sigma, that's now your decay rate on your exponential. You now have an e to the minus sigma t damping or decaying this response, and the omega sub d actually gives you the damped frequency of oscillation. What you may not remember is whether you were dealing with a sine or a cosine. This one, because there's no s in the numerator, is a sine, and it's now sine omega sub dt. We're doing the one-sided Laplace transforms. That is now our expression for the inverse Laplace transform of some constant over s squared plus something s plus something else, where we factored that denominator into s plus sigma quantity squared plus omega sub d squared, and you could do that by completing the square if you wanted to. I guess I could ask for a show of hands who got that right, but I won't embarrass or put anyone on the spot. Let's then give it a second go. Suppose now that I said, what's the inverse Laplace transform of, let's say, y sub b of s? So now this special structure, if you remember the cosine, it's s over s squared plus omega squared. That's just the cosine. This is now a damped cosine. This is now a pure damped cosine. Is now the decay rate is the same, and the frequency of oscillation is the same, because our poles are exactly the same at the same location. We now still have in the S-plane we have these poles at minus sigma plus and minus j omega sub d. Now what we have is we actually have a zero right there. And that now led us to this cosine waveform that's exponentially damped. In the time domain, if you needed to sketch this, what would that look like? At 0, what value do you have? You have two parts, an exponential damping part and a oscillating part. At 0, cosine of 0 is 1. E to the 0, 1. So we're actually, in this case, starting at 1. And if it was just a cosine waveform, then it would look like that. But it's actually exponentially damped. By that e to the minus sigma t piece. This is our cosine piece. And if we needed to, we could actually find that omega sub d by looking at what is my period of oscillation. Now, what we're doing is we're actually point by point multiplying those two pieces together, and that now gives us, I'm going to fail miserably at my sketch, but I hope you can envision I need to just connect the dots. I need to go through there, and then I need to, let's say, go there, there, there. So I'm wanting to what? I told you it's a Monday morning. I'm just making sure you guys are awake. The blue curve is then this decaying exponential. Is that a little bit better? And it's impacted by the real part of the two poles. That gives us how fast it's damping. And it's influenced by how much it's oscillating by the cosine piece. Now, what happens if I give you a third expression? Let's say the inverse Laplace transform of AS plus B over S plus sigma squared plus omega sub D squared. What does that look like as a function of time? And A and B, I haven't told you what those are. Those are just generic variables. Where are your poles? Same location, isn't it? And those poles earlier gave us a sine or a cosine that was exponentially damped. And we knew how much it was damped. That was given to us by the real part. And how fast it was oscillating was given to us by the imaginary piece, how far away from the real axis you were in the vertical direction, your omega sub d. Those together gave us the exponentially damped sine and cosine. Now we don't necessarily have this numerator, we don't necessarily have this numerator for a pure sine or a pure cosine. What do we have? Some combination of the two, right? So now we have a sum, and we don't know yet the relative magnitudes of the sine piece and the cosine piece, but we have an exponentially damped sine and cosine together. How could we see that? If we look at the numerator, we could say, well, that's AS plus B. But I know that that could be written as some linear combination of a cosine exponentially damped and a sine exponentially damped. A and B now, let's say I know those. I know sigma and omega sub d by the denominator. I now have two equations and two unknowns. Where are my two equations coming from? If I multiply that out, now I can simply equate coefficients of like powers of s. I can look at all of the different s's. I could have an s squared, an s to the 1, an s to the 0. In this case, I just have an s to the 1 and an s to the 0. Those two powers of s have coefficients. I can equate the coefficients, and since I have an s to the 1 and an s to the 0, I have two coefficients that I can now work with. I can now equate my coefficients for s, which says that a is equal to alpha 1. I now know how much of the cosine that's exponentially damped I have. That's going to just be what a was. And then if I equate the s to the 0 coefficients, I know b, I know sigma, I know omega sub d, I now know alpha 1, that's just a. The only unknown there is beta. I can now find out how much of the sine piece I have. Or solving for beta sub 1, I have b minus alpha 1 sigma over omega sub d. Now that I've given you that information, can you tell me what y sub c of t looks like? That's just some amount of the cosine, an alpha 1 amount, e to the minus sigma t cosine omega sub dt, plus some amount of the sine. And that's now one way of writing this time domain response from the starting transfer function or frequency domain expression for capital Y sub c of s. Questions on that? That's not very easy to see, is it? I couldn't even sketch very well the one piece. Now I need to sketch the other piece and add them up, point for point. That's kind of hard to do mentally. But you could also write this, since the sine and the cosine are both oscillating at the same frequency, you can combine those into either a cosine that's shifted or a sine that's shifted. And they're both exponentially damped at the same amount. Meaning this equation could be written as, let's say, an a1 e to the minus sigma t cosine omega sub dt plus, let's say, b1, or we could say an a sub 2 e to the minus sigma t sine omega sub dt plus b sub 2. And you could sketch the pole zero diagram for that transfer function, or for that particular ratio of polynomials of s. You have a zero, a finite zero at minus b over a, and you have your poles at the same locations. So you know where the poles and zeros are. All right, now suppose that somebody says, well, you just gave me a frequency domain expression. What if I applied a step to a second order system? In other words, what if you were asked to find the inverse Laplace transform of alpha s plus sigma squared plus omega sub d squared, that's now meaning this piece, part of that alpha, some of that alpha could actually be a part of my command. If I had the unit step, then alpha is just part of my system. But what I've shaded in yellow highlight is sort of a transfer function of a second order system. The step is the 1 over s piece. What is this going to look like in the time domain? This whole expression, we could say, is capital Y sub d of s, and we want to know what is the structure of the time response. Do you have a feel for what that is? Or what that might look like? We've now put one more s in the denominator. We've hit a second order system with a step. You can do a partial fraction, exactly. Then what happens? A piece of your partial fraction will look like what you just were doing in parts A, B, and C. The other piece is going to look like something over s, isn't it? So you now have a constant in the time domain with this exponentially damped sine and cosine. Those combined, that's exactly what you have. And you can mentally grasp that by simply doing a mental partial fraction expansion. You can go, oh, I know what one of those pieces looks like. We just talked about it, the first three pieces. The other piece is the easy one. That's the something over s, which says then that you immediately know what the structure of this expression looks like. You now can say in general that y sub d of t is some constant a sub d plus b sub d e to the minus sigma t. I'm going to pick the sign because that's what we're going to be using throughout. Omega sub d, that's the same vertical distance or the imaginary part of your poles. The sigma was the real part. Let me call this now some angle c sub d, t greater than or equal to 0. What's that look like in the time domain? A damped oscillation shifted up, essentially. Now we have something that's approaching a constant. What constant is it approaching? A sub d. And it's approaching that just like our previous sketches did with these exponentially damped sines and cosines, which means that we now could sketch this like that. And how fast is it collapsing? What's this? Running out of colors. That you could sort of envision This collapsing down, that's influenced by what parameter? E to the minus sigma t. How fast is it going between peaks? Or how often is it doing that? That's now our damped period of oscillation, T sub d. But T sub d, if we knew that, or what's that related to? Omega sub d, isn't it? Omega sub d is 2 pi f sub d, which is 2 pi over T sub d. So if we could physically, what are we doing? We're actually going into the lab and shaking a second order system, and it's going to respond like that blue curve. We want to now extract from that blue curve parameters that will allow us to identify this second order transfer function that I circled in or highlighted in yellow. We're trying to find the omega sub d, we're trying to find the sigma, and we're trying to find the numerator of that second order transfer function. Meaning, if we know y sub d of t, can we find g of s? Maybe I should have done, let me change this. Can I say that's an alpha bar? It's now a fish with a hat on, or a bar on top. Now I want my g of s to be alpha over s plus sigma squared plus omega sub d squared. This is our underlying system. That's actually a second order system, and we want to be able to identify those parts. We want to be able to find the numerator, we want to be able to find the denominator, which is made up of, if it's an underdamped response, it's made up of a real part and an imaginary part, sigma and omega sub d. And we can actually do that. Let's now look at what we have. What parts of this time domain response, y sub d of t, can tell us about this second order system, g of s? Meaning we could have this either as a time domain response that we have the data for. Maybe we've now identified this y sub d in the time domain as a formula. If we have it as a formula, what's a sub d going to help us figure out? If we know capital A sub d, and I know how much I've pushed my system, in the lab you're going to push it how far? 2,000 counts, which is about, it's between 1.5 and 2 centimeters, if you're thinking centimeters. So it's going about the width of your thumb. That's about how much we're displacing this mass. And it's shaking around that displaced location. Then we're releasing the step, and it comes and oscillates back. Then we hit it again, and then again, 3 times. What would a sub d allow us to compute or provide us insight into relative to this second order system g of s? Any ideas? If I push it 2,000 counts and it goes 1,000 counts, what do I know about my system if it eventually settles at 1,000 counts? Do I know any property of my system? If I pushed it 2,000 counts, if I said go to 2,000 and it goes and it settles at 1,000, What do you know about your system's transfer function? There's an error. Well, it's an open loop system, so we aren't comparing it yet. Well, we are. We're saying, I told you to go to 2000 and you only got halfway there. What's that tell you about the system's properties? I'm not wanting to give you the answer. I want to, but we don't know yet if it's underdamped or overdamped. It's just settled at a particular value. What happens when it settles? We've gone to infinity, so you have to spend a lot of time in the lab. These labs are long. You have 3 of them, so you have 3 infinities to wait. What's infinity? To infinity and beyond. What's infinity? How much is infinity? Please, you're killing me. How long is infinity in electrical? 5 time constants, exactly. What's 5 time constants? Well, that's going to be influenced by our damping, isn't it? So 5 time constants, if one time constant is 10 milliseconds, we have to wait 5 of those, 50 milliseconds. We're done. We're at infinity. That's a big infinity, or short infinity, isn't it? Here we have a mechanical system, so it may take a little bit longer for our time constants and 5 of those. But now we've gone to infinity, and we've seen that our system now is at 1,000. What's that tell us about the system property? We put in 2,000, it just jumped to 1,000. It didn't jump all the way to 2,000, it just went halfway. What do you know about what that system is doing? If somebody gives you A sub D, and they tell you how far you tried to push it, what's the difference? Or what's the ratio? What's the gain? Right? There's a system gain. You pushed it 2,000, it only got to 1,000. What's the system gaining that input signal with? 1/2. You now have a DC gain of 1/2. And that's going to be related to your alpha, isn't it? It's not going to equal alpha if you've pushed it a certain amount for more than just 1. But A sub D now is going to be related to the DC gain of G of S. What's the DC gain of G of S? Here. How do we find the DC gain of a transfer function? What's the frequency of DC? 0. What's S? That's a frequency. It's 0. If we let S equal 0, we'll have DC, won't we? If we don't have a pole at the origin, we're going to be okay. And we don't have a pole at the origin. We have 2 poles at minus sigma plus and minus j omega sub d. If I put S equal to 0, I now have alpha over sigma squared plus omega sub d squared. That's my DC gain. So if I knew sigma and omega sub d, I could find alpha if you give me the DC gain. And in my example, I said that DC gain was what? I said, go to 2,000. It said, I'm going to go to 1,000. The DC gain was 1/2. So now you would set alpha over sigma squared plus omega sub d squared equal to 1/2 and solve for alpha if you knew sigma and omega sub d. So we need to find those guys. If somebody gave you, so the first thing is you can find the final value of your transient and use that to find your DC gain of your system. What if somebody now measures between those oscillating peaks in your response and What's that going to be related to? If I give you omega sub d, where's that going to be? It's going to be omega sub d, isn't it? That's going to be your imaginary part of your poles. And how do you find omega sub d? Well, you could measure T sub d. In the lab, some of these systems you don't give them much of a push, and they may only have one bump before friction takes over. And so we're going to start looking at finding the time to peak and using that to infer what omega sub d is. Meaning, if somebody now gives us omega sub d, or how do we find that? That's actually found from the damped period of oscillation, or omega sub d will show is related to the peak time. So if we can now measure the period between bumps or maximums, or if we can measure the peak time, we can now figure out what omega sub d is. So all of these are sort of giving us the information in the frequency domain and the time domain. If I gave you sigma, what would that be related to? Or if I needed to find sigma, how could I find it? You could measure the time constant, and you can get the time constant by measuring your settling time. That's one way to do it. So this is now related to the settling time, and we're actually going to probably, because some of these, the nonlinear properties of the system will overtake the true, or let's say the ideal second order response. So we're going to maybe try to measure the damping. And we can do that by looking at the percent overshoot. And all of these relationships are examined a little bit more carefully in the demonstration number 1 and in the notes of demo number 1. Let's now see if we can start to put together some of those pieces in the time that's remaining. Let's develop some terminology. We're trying to identify this system G of S. It's a second order system given by alpha S plus sigma squared plus omega sub d squared. That's what we're hoping to identify. And relative to that, we have this S-plane picture, where the picture is influenced by these two complex conjugate poles, where the distance they are into the complex S-plane is sigma, so that this point is actually minus sigma. This vertical distance, or the imaginary part, is omega sub d, so that this location is now j omega sub d. And a lot of times we don't even look at the bottom half. We just cut off and look at the top piece. And relative to this top piece, depending on, well, if you have sigma and omega sub d, can you tell me anything about the distance that pole is from the origin? Somebody's theorem. Pythagorean theorem, isn't it? That's the hypotenuse of a right triangle. So we know sigma, we know omega sub d, we can get that distance or the hypotenuse, and this length is omega sub n. That's the natural frequency. Omega sub d is our damped frequency. And we will also look at this angle theta. And we might even reparameterize sigma in terms of zeta. And what's zeta? Well, if I said sigma is zeta omega sub n, and the hypotenuse is omega sub n, can you tell me anything about the cosine of theta? Cosine of theta is adjacent over hypotenuse. It's zeta omega sub n over omega sub n. Cosine of theta is our damping ratio. So if somebody says, give me the damping ratio zeta, if you know where that pole is, you can now find the angle associated with that pole and calculate the angle zeta. So that theta is now, if you needed to find that from the damping ratio, you could find that also. So we have two complex poles with a real part of sigma minus sigma and plus and minus j omega sub d. And we can relate omega sub n, sigmas, and omega sub d's by using the Pythagorean theorem. A squared plus b squared equals c squared with the appropriate a, b's, and c's. So that now our g of s, we are going to parameterize that many different ways. We could say it's alpha over s plus sigma squared plus omega sub d squared. That would then be the explicit structure identifying the real and imaginary parts of our poles. We could also, if we wanted to, we could multiply that out, and we now have s squared plus 2 sigma s plus sigma squared plus omega sub d squared. And somebody else or some other textbook might write this second order transfer function as an alpha s squared plus 2 zeta omega sub n s plus omega sub n squared. And hopefully now you can see how those pieces are related. There is our sigma piece. And the natural frequency, that's the hypotenuse. Squared is equal to a squared plus b squared, where a is sigma and b is omega sub d. So this piece corresponds to that piece. And we're going to be throwing these different descriptions or parameters around. We might say, what's your damping ratio? Or what's the natural frequency? Or what's the damped frequency? What's the damping? So you need to know where all of these are coming from, and hopefully you can simply sketch your S-domain plot and come up with what you have. What we're wanting to do then is identify that system by exciting it with a step. Here is our block diagram. We have our system, G of S, with some applied input producing an output. We now know that y is equal to g of s times r of s, and r of s, we're going to let that be some constant amplitude waveform, where a is now the amplitude. In the lab, it's 2,000. It's 2,000 counts. If we put this all together in our parameterized form, y of s is now g of s, which we could write many different ways. It's alpha s plus sigma squared plus omega sub d squared times r, which is a over s. Now, that's a little bit messy maybe in terms of parameterization. Can I mess it up a little bit more? Sure. I can multiply by 1, can't I? That won't change anything, but my 1 that I want to use is a special one. Omega sub n squared over omega sub n squared, which now allows me, if I put these pieces together, I'm really wanting to find now an expression that is simply omega sub n squared over, and this piece right here is omega sub n squared, isn't it? And so I'm going to have s, which is this guy, and then the denominator, s squared plus 2 zeta omega sub n s plus omega sub n squared. What's in my leading black box? In the blue denominator, I have accounted for s, and I've accounted for the first second order polynomial. I haven't accounted for that red omega sub n squared. What else have I not accounted for? I have an a, and I have an alpha. That's just a constant number, isn't it? And all of my dynamic information is actually contained right here, and I'm going to call that y bar of s. That expression is going to be easier to work with. This piece is just a scaling. Meaning, I could now sketch, may not be very accurate, but I could sketch y of t and y bar of t. And what will they look like? Suppose I do y of t in blue. This is y of t. Well, maybe I should make that in blue. And maybe I let y bar of t be a scaled version of y of t. Y bar of t is easier to play with, but if it's sketched properly, it's going to peak at the exact same time, isn't it? So this will be my peak time, t sub p. I will have a y bar of t sub p, and I will have a y of t sub p. Those will be the same. And I will have a final value out here, a y bar final value. Do you see what that will be by applying your final value theorem to that black boxed expression? What's it going to go to? S times that and let S go to 0. What do you get in the black box on the right? I scale it by S, so that one S in the denominator is gone. Now I let S go to 0. So I get omega sub n squared over omega sub n squared, which is just 1. That's why this is a nice expression. This is now 1, and this is some scaled version up here. Y final value is some, let's say, in the lab, I think we call that A1. We now have the time to peak. We have the final value. We're going to get our damping from those, and we'll pick up at this point on trying to identify our G of S from this information the next time. But you can preview that via Demo 1.